So the directional derivative is a very interesting and powerful tool in vector calculus. Basically, the idea is, if you think about it, if we look at any surface, f of xy or f of xyz, for instance, then or any surface represented by this. So basically, what we know is what is fx. Fx is the change in the x direction, or along the x-axis. Fy is along the y-axis, and Fz is along the z-axis. So these are three specific directions, and if we look at the change or the derivative of the function f of x, y, z in these three directions, fair enough, straightforward along x, y, and z. But what if that's not what we're interested in? What if we're interested in, for instance, if you had a temperature map and you had a function representing temperatures all over different longitudes and latitudes? What if you wanted to find the derivative in the northwesterly direction? Not along north, not along south, not along west or east, but rather northwesterly, for the sake of argument, okay? Or in a particular latitude or longitudinal combination. What if you wanted to find that particular change in temperature along that, or the speed of the wind in that in that direction? Now, in order to do that, we use this very powerful tool called the directional derivative. So the directional derivative basically is about that you have a function f, and at a certain point, x0, y0, z0. So you're at a particular point on this this function, and you say, I want the directional derivative in the direction of a unit vector, because we're not interested in the size of the vector, we're only interested in its magnitude. So ABC is some unit vector. So this is a unit vector. Okay, it's a unit vector. So what I want is, at the point x0, y0, z0, I want to know how does f change in the direction of this unit vector u. The way to calculate this, first of all, with the notation we use is as follows. It's the directional derivative of of f at x0, y0, z0 along the vector u. Okay, and its formula is it's very straightforward. So here, if you take the dot product with the gradient at point x0, y0, z0 dot with the u. So its definition is the directional derivative is simply the dot product of the gradient with the unit vector that you're interested in, and that should give you the directional derivative. So, quick example. Let's have a quick example here. So let's look at an example. So here's a question. Find the directional derivative of f at 130 in the direction of v equals 1, 2, minus 1, where f is, of course, this x sine yz. Now, in order to do this, one of the things we need to calculate, there's two things. We need the gradient, of course, at 130, and we need our unit vector. Now remember, this is a vector v, and we're not interested in the vector v. We want to isolate the direction of v. So that means we're going to have to normalize it. Let's do that in a second. First thing we need is to calculate grad f. So grad f is going to be the x derivative of f, first of all. So that's going to give me sine yz here. Then it's the y derivative, so that's going to give me x z cosine yz. Okay, and the z derivative is going to be x y cosine yz. Okay, so first of all, that's my grad. That's my gradient. Now, let's move further. Now we'll calculate grad f at, of course, 130. So that means, essentially, 130 means x is 1, z is 0 here, so sine of 0 is 0, cos of 0 is 1, but since 0 is 0, this is also 0, and here you'll have x, y is 3, and cos 0 is 1, so you end up with 0, 0, 3. Okay, so remember here, where this is your x, this is x, y, and z. So you have to substitute them carefully. See here, all of these are z's, and that means you have cosine 0 and sine 0, essentially. Okay, so just to help you understand how I got the 0, 0, 3. Next, what we need to do is to normalize V. So what we're going to do, normalization means our unit vector that'll come from V is basically V divided by the norm of V, which means 1, 2, minus 1 divided by the square root of 1 plus 4 plus 1, so it's equal to 1 over square root 6, 1, 2, minus 1. Now what I'm going to do is I'm going to take the dot product. So the directional derivative of f at 1, 3, 0 is simply the dot product of 0, 0, 3 dot product 1 over root 6, 2 over root 6 minus 1 over root 6. Now when I take that dot product, it's going to give me 0 plus 0 minus 3 over root 6, which is just square root 3 over 2, negative of course. So that is my directional derivative in the direction of the vector 1, 2, minus 1. So first step, calculate the gradient, which has x component, the x derivative, y component, y derivative, and z component is the z derivative of f. Then calculate that at 1, 3, 0, the given point. Then next, normalize the vector, so you get a unit vector. We get that, and then you take the dot product with the gradient at the value, at the point, and that gives you your directional derivative. I hope that's clear. So one other point we need to look at when it comes to the directional derivative is when one looks at the directional derivative, that means that essentially you're standing at a point and you're looking around you and you say, well, okay, look, I'm at this point and these are all these different derivatives that could be calculated, and there's many more than the ones I'm drawing. In fact, it could be a direction, in any direction you could calculate the derivative, and what you want to know is which one of these from this point, which derivative is the maximum, basically. All right, what is the direction of maximum increase, in other words? So in order to calculate that, if we look at the definition grad f dot u, that's really what we're really saying there. Is the other definition is that it's the norm, or the magnitude of grad f and the magnitude of u cosine theta. Okay, now if in this case u is a unit vector, so this just boils down to grad f cosine theta. Now what is the largest? We know that cosine theta is somewhere between -1 and 1. And if we go for its magnitude, okay, so if we go for its magnitude, that means that cosine theta is something less than or equal to 1. It means the largest it can be is 1. Now when is it 1? We know that it's equal to 1 when theta is equal to 0. So if theta is equal to 0, then that means that we end up with this becoming cosine of 0, which is 1. So the direction of maximum increase is in fact grad f. Now the question then is, that's the magnitude of it. That's the maximum possible increase of f. And the question is, in which direction? Now if theta is equal to 0, that means the vector we're looking at is grad f. And its dot product with u is 0. So what is u? Because u will tell us in which direction it's changing. So if you think about it, it's quite clear. If theta is 0, that means the angle between grad f and u is 0, which means they're in the same direction. So it means the direction of maximum increase, okay, is grad f. So it's along that. It's along the vector grad f, in fact. So it's in the direction of grad f, and the maximum maximum value of du f, or the direction derivative, is grad f itself. So its maximum value is this, and its direction is in the direction of grad f. So it's the direction of maximum increase. Okay, so if as an example, very quickly, if we were asked, here we have a question and says f of xy is xey, and we're standing at the point 2, 0. So in what direction does f have maximum rate of change and at 2, 0, and what is the maximum rate of change? So that simply is grad f, first of all, calculated, turns out to be it's ey and it's x ey. That's our gradient. Now grad f at 2, 0 is simply e to the 0 is 1, and this is going to be 2. So it's 1, 2. So according to the theory we've just looked at, the direction of maximum rate of change is in fact 1, 2. It's grad f at 2, 0. And the magnitude of this, so the magnitude of grad f 2, 0 is the actual maximum rate of change. So that's the magnitude of 1 squared plus 2 squared, so it's equal to square root of 5. Okay, so that's the maximum. That's the maximum rate of change. That's the maximum something can increase if you're standing at 2, 0, and the direction you go is the direction of grad f, gradient f. All right, we'll stop there.